Okay, in this particular video, I want to discuss just some more examples. These are examples that I've handwritten for my classes over the years, and so we'll just step through some examples. The first thing I'd like to talk about is the use of the step function command. So I have a figure here that just shows a step function or a piecewise linear function. So you can see it's got the ramp and the second ramp and then the third ramp. And if we were to write this out longhand, we would have to basically get an equation for each line. And then each line would have a range of times over which it was valid. So for example, we would have some function f1 that would be equal to the equation of this line, which is 2t. And then we would have a function f2 that would be equal to the equation of this line, which has a slope of -2 and would have a y-intercept of 4 if we were to calculate that. So that equation would be valid from t equals 1 to t equals 3. And then we would have a third equation that consists of the equation of this line, but once again, that's only valid from 3 to 4. So longhand, we're writing the equation of each line, and then we're writing a time range over which that's valid. The step function notation allows us to shorten that a bit by using step functions, and so what we can do is we can write this mathematically without having to specify a range, because the step function itself specifies the range. So we would take this function f1, which is valid from t equals 0 to t equals 1, and we multiply that by a window that's created by step functions. So we have u of t minus u of t minus 1. And this should be a u here. That's just a misprint. And then, so the u of t actually turns this function on at 0, and the u of t minus 1 turns it off because it's subtracted at 1 second. And then we have the equation for this line that's valid from 1 to 3, and we window that with u of t minus 1 minus u of t minus 3. And then we have this equation that's valid from 3 to 4, and we window that with u of t minus 3 and u of t minus 4. So what you would do to obtain a complete expression is plug in f1, f2, f3 into each of these. Now the Laplace transform definition. So that's just an example of how to use a step function. So this Laplace transform definition, we all know. It's whatever our function in time is times e to the minus st. It's called a single-sided transform, which is what we use in electrical engineering because we're always concerned with systems that have causality in a linear systems or linear circuits class. So the system has some, initial condition and turns on at t equals 0. So just stepping through some examples of how to take a Laplace transform. The first example is the Laplace transform of the impulse function. You can use the property of sifting of the impulse function that says we're going to select the value 0 since this is del of t minus 0. We'll plug that in for all of the t's in this expression, so we'll get e to the minus 0, which is basically 1. The transform of the time-shifted impulse, we basically do the same thing. We use the sifting theorem again, only this time we'll evaluate everything else in the integral at time t0, so we get the e to the minus st0. The step function, similar. We basically plug that into the integral. The step function, remember, is 1 for t greater than 0, so we can substitute a 1 here. And then that allows us to do the integration, which is pretty simple integration. We fill in the limits, and we end up with the transform of the step function is 1 over s. And then we can do the time-shifted step, which basically means the step function doesn't turn on until some t naught. So what that effectively does is change the integral limits. We start at t sub 0 instead of 0. And so then when you evaluate at those limits, you get e to the minus st0 over s. Now the exponential function, and just a note here that remember we are working only with the single-sided transform. So when we say we're finding the transform of e to the minus at, we're implying that that's actually e to the minus at times u of t, because obviously e to the minus at would have values for negative time. So once again, then our integral runs from 0 to infinity. Here's our function e to the minus at. Here's our transform kernel e to the minus st. And so you can do a little algebraic manipulation and come up with the result that is 1 over s plus a. The sinusoidal function is a little bit different. Once again, this would be the transform of sine of omega t u of t. You could look this integral up on a table if you have an integral table handy. These integrals are available. If you don't have a table, it's very simple to use Euler's relation. So this expression here on the second line is Euler's expression substituted for sine of omega t. We can then collect some like terms in the exponential, combining the e to the minus st with the first and the second term. Integrating then and evaluating at the limits from 0 to infinity, we get the following expression. And then if we find a common denominator and combine these two terms, we get this expression here, and the j omegas will add in the numerator to give you 2j omega over 2j. So the j's and the 2 cancels out, the s's cancel out, and this ends up being our expression. You can do the cosine function in exactly the same way. There you have 2 in the denominator in the Euler's expression, and you have an s that ends up in the numerator. So there are some properties of transforms as well. First of all, the transform is linear, which means if a function of time is multiplied by a constant, the constant comes out, and you just take the function of time, you take its transform. It also means that the transform of the sum is the sum of the transforms, so as long as things are added, we can take their transforms individually. This is sort of that underlays the whole principle of superposition that's so important in electrical engineering and other engineering. However, we would note that the transform of the product is not the product of the transforms. The product of the transforms comes if we have a convolution between two time domain functions. So this multiplication is a nonlinear operation, so it doesn't hold when the transform is taken. The property of differentiation is the one that's so important in differential equations. Basically, if we have some function and we have its time derivative, the transform of the time derivative of that function can be found by substituting df dt into the formula for the Laplace transform. We can then integrate by parts, assigning u as e to the minus st and df dt as dv, and then dt is df. So making that substitution, we end up with e to the minus st f of t for uv, and then we have to evaluate that at our limits, and then we have minus s e to the minus st f of t dt for our second term. So the first term is just evaluated as the initial condition at 0, because at infinity e to the minus st goes to 0. The second term, the s can come out. You have a double negative. The s can come out because with time integration, s is a constant. And then what we're left with under the integral sign is just f of t e to the minus st dt, which is the transform. So when we take the derivative of a function in the time domain, that corresponds to multiplication of the transform in the s domain with the initial condition subtracted off. Higher order derivatives hold. There's a pattern. And so if you look, the second order derivative is s squared f of s minus s f of 0 minus f prime of 0 minus. So you are adding initial conditions for each order of derivative, which makes sense because we would have to solve one condition for each order of derivative. Integration, we can do a similar thing. Without going through it in great detail, you basically want to integrate by parts here as well. And when you do that, you get f of s over s. So integration in the time domain corresponds to division by s in the s domain. So basically, these two properties, their physical meaning or their significance is that you transform differential and integral equations into algebraic equations with polynomials. You can then solve those equations, inverse transform back into the time domain, so you've effectively solved differential equations, including inhomogeneous part of the differential equation and the initial condition. So it's very handy to be able to do that all at once. There are some other properties that are less important in this course that are pretty important in a linear systems course. One of those is the time shift. So it is kind of difficult to model time shifted problems that don't begin at t equals 0. So the nice thing about this property is that we can basically take the transform as if there were no time shift, and then multiply whatever the result is in the s domain by e to the minus as, where a is the number of seconds in the time shift. Frequency shift is similar if you have multiplication in the time domain by e to the minus at. That corresponds into a shift in the Laplace domain by the value a. So we have this f of s plus a. So basically you would take the transform of whatever f of t was, and then to incorporate the fact that you had multiplication by e to the minus at, you just go into your result, and everywhere you have an s, you replace it with an s plus a. Okay, and we're going to skip over scaling. Basically, your approach is you're going to have a table of transforms and a table of properties, or maybe it's all one table. And these two combined would give you the solution to most problems. So most problems could be looked up on the table. And if you don't have a complete table, you can sometimes use a combination. So for example, a lot of tables will include this entire expression, so you don't have to do anything else except look up the result. Let's suppose your table only has cosine of omega t. Then you can take advantage of the fact that multiplication by e to the minus at results in a shift of s. So the transform of the cosine of omega t is given by s over s squared plus omega squared. If we have multiplication by e to the minus at in the time domain, all of our s's are going to move to s plus a, so the final result looks like this. So those are just some pretty fundamental examples of the Laplace method, the Laplace transform, and where